which is one of the main topics of this conference and meeting. So it's very well timed. So without further ado, let's have Nonabelian action for M5-branes.
Thank you. This talk is based on, is the mic working? Yeah. This talk is based on two papers I have written. One paper which is written recently, just put on the web last Monday, and then an earlier paper last year. So this talk will consist of 4 parts. I will introduce the subject, and then my construction of the action for multiple M5-branes will be based on the construction of Perry and Schwartz. So I will spend some time reviewing their construction, explaining the special feature in their construction. So what's the reason to study M5-brane? We know a little bit about M5-branes. So M5-brane exists in M theory, and its low energy volume dynamics is given by a 6-dimensional superconformal field theory with 2,0 supersymmetry. And so we know the global symmetry. There's a supersymmetry, and there's a conformal symmetry, and there's a R symmetry. And also we know the spectrum. This can be obtained by looking at supersymmetry, and you only have this kind of multiplet, which is a tensor multiplet. Tensor multiplet here means you have a gauge field, which is a second rank gauge field, whose field strength is self-dual. It's a self-dual tensor. Also, you can obtain the multiplet by looking at supergravity solution, looking at zero mode analysis, and then you get the same conclusion. But there's a lot of things we don't understand about the M5-branes. So first of all, we don't know what kind of gauge symmetry governs a system of multiple M5-branes. So if you put a number of D-branes together, we know there's an enhanced gauge symmetry. U1 become UN. But we don't know about whether this happened or not, or how this happened for M5-branes. In fact, we don't have any independent channel to know about this. I mean, the string duality we are talking about always tell you there exists a theory, but without telling you what kind of gauge symmetry it is. Also, we know the M5-brane, when you put them together, then of course it's interacting. So there's an interacting self-dual system there, and that's also difficult. Apart from these 2 problems, there are also other problems which I have also, one of them I have also worked on. For example, if you have a D brane and you put a B field, NSB field, then we know the geometry is deformed and become this well-known Moyal type geometry, commutator equal to a constant. So recently, with another student, we have looked at this a similar system for M5-brane in the C field, and then we have some result. I think it's for another talk. But what we find is actually it's quite interesting because the corresponding geometry is like this one, but it's given by a Lambout 3 bracket instead of a 2 bracket, and the Lambout 3 bracket become a constant in that case. I have nothing to say about entropy, but obviously that's an interesting problem because it's very difficult to understand how come you get an n cube. Right? If you for M2 brane you get n3 half, which is easier to understand because n squared become n3 half is somehow easier. You can say you have some bound state or stuff. N cube is difficult, more difficult. But I understand. But there are some progress recently from index argument. So let me comment about these 2 problems about the symmetry and the self-dual dynamics. So first, the gauge symmetry. So if you put D brane together, so it's supposed to be different color here, but I don't see any difference in color here.
I see difference.
You see difference in color, okay.
The commentators are red.
My wife always complain about my vision, in fact, yeah. So, okay. So, well, in fact, I have, I don't want to say it in public, yeah, okay. So,
this is being recorded, you know. This is being recorded.
I know.
She can download this later.
Yes. When you go to the Nonabelian case, you just have to put this commutator term. The symmetry is promoted in a very simple way by including this commutator, which is governed by structure constant of Lie algebra. For single M5-brane, we know the theory has a symmetry. It's just a tensor gauge symmetry parameterized by a one-form parameter lambda mu, and the transformation keep the field strength Riemannian, just like the U1 transformation for Maxwell gauge field. if you try to think about it a little bit and you try to play with it, then you say, okay, when in the non-abelian case, I put a indices A, which tell me how many number of B field I have, and then I want to basically non-abelianize this formula here. But then immediately you see there's a problem because the parameter has a indices. So whatever you put here, you have to put at least a lambda here, and then because B has an even number of indices and the lambda has one indices already, so there's no obvious way you can put anything here. And also for the field strength, it's also not clear what you put, because in the abelian case you put A and A. Obviously, if you put B and B, you get too many indices. So again, it's not clear how you can do it. But after having tried this, then you realize, in fact, it's not even clear. You have to do something like this, because nobody tells you whether the Coulter symmetry has to be behaved in the non-abelian in the non-abelian case. The only thing we need to know is that the theory eventually has some non-trivial self-interaction. So the case symmetry in the Yamil's case is non-abelian, but in this case it turns out in the construction I will explain, the tensor case symmetry will be abelian, even though the interaction is still fully nonlinear and fully interacting. So I will not talk about Jabs in this talk, and I think it's an interesting mathematical subject, but it's just I didn't know anything about it, so please don't ask me anything about Jabs. Okay, and the second problem is self-deal dynamics. It's well known, I mean, since maybe more than close to 20 years ago. In '84, well, maybe even earlier, but this is a paper I know about. Self-deal dynamics is difficult. If you want to have an action describing self-deal dynamics, is possible, but then you have to sacrifice Lorentz symmetry. So in this paper here, they consider self-deal boson in 2 dimensions and self-deal Yang-Mills, etc., etc. And what they find is that you need an action which has you don't have manifest Lorentz symmetry, but you have some modified Lorentz symmetry. And for the single M5 case, in which you have a free theory, so at least you don't have the problem of interaction. You just have a free self-deal dynamics. You want to write down action. That is possible. So that problem was solved by Perry and Schwartz, and also Hanot and Tittelbaum. They have also looked at this problem, but not for M5-branes for obvious reason, but they look at it from the point of view of P form, self-deal P form. So it's possible to write down a self-deal action, but without six-dimensional Lorentz symmetry. So I will review this later. And then a little bit later, basically a few months later, PST, Pasti, Tonin, and Sorokin, they were able to provide covariant description in which, depending on the gauge fixing you choose, you can reproduce either this or that. Right? So it's like a unified description of this different formulation. But it's not clear, not no clear. It's not clear how to do this for the non-abelian case. In this talk, non-abelian just means n greater than 1. Because of these two problems, we don't know how to generalize the tensor case symmetry, and also we don't know how to write down this non-abelian self-deal dynamics in terms of an action. Moreover, there are local theorems in the literature which say that if you keep the locality of the action and the locality of the transformation law, then you cannot have any non-trivial deformation of the abelian two-form theory. But precisely because of this local theorem, it suggests that the important direction to go around is to introduce non-locality in the theory. So in my construction, you will see non-locality, but there's also a very physical reason for that. So I will explain that later. So before I jump to my construction, I will just comment about the literature. So this problem has also been looked at recently by a different number of people. So from the world volume theory point of view, considering the action, so Ho and Hong and Marceau, they have considered a action with with a compactified circle. So that problem was solved, I mean, in this case, with a circle compactified. But you may still wonder whether you are certainly interested in M5-brane in fast space. So we would like to do that also. That's one of the motivation for my work. And this paper look at look at the problem without touching the self-duality, because the self-duality is assumed. Is implemented at the equation of motion level. They were not interested in an action which reproduced the equation of motion, which is self-dual. But even so, they were able to write down the supersymmetric conformal field equation, which is quite interesting. This paper, which I wrote last year, I tried to decompose the problem into two parts. So to construct the dynamics, first I want to have a formulation which tell me how to do gauge transformation, and then I look at the self-dual dynamics. So this is like part one of the construction. So in that construction of the tensor gauge symmetry, I have to introduce a set of gauge boson transforming with respect to G cos G gauge group. So this is the reason why I have this G cos G gauge boson is because this is argued by looking at open membranes, ending on M5-branes. Open membranes here, I was using ABJM open membrane, so there's a G cos G there already, UN cos UN. And the Chern-Simons in the presence of boundary is not gauge invariant, so that will introduce some anomaly. And to cancel the anomaly, that means on the M5-brane, that the boundary of the M2-branes, which means on the M5-brane, you must have some term which cancel this anomaly. And if you look at the descent formalism, this is precisely the Western-Milnor term. So you have a Western-Milnor term on the boundary, and this Western-Milnor term, as usual, generate Kasmuti current algebra. So you have a Kasmuti current symmetry on the self-dual string, which is the boundary of open membranes. And then whenever you have on the well sheet, whenever you have a Kasmuti symmetry, then well, I don't have a strong argument, but at least we know in heterotic string, if you have a Kasmuti symmetry on the well sheet, then you can have a vertex operator construction, which tells you have a space-time gauge symmetry. Right? For example, you have EA cos EA Kasmuti symmetry, then that gives you space-time gauge symmetry. So here I'm just making the analogy. I don't have because we don't have good control about self-dual string theory. So that suggests the existence of this G cos G gauge symmetry in the M5-brane. So I take that as an input, and then one can construct this tensor gauge symmetry. Yeah, certainly.
So when you've got that boundary of open M2s,
well, you work on it also,
then you could also, there's a choice to be made, where you could cancel the anomaly, like you say, or you can impose boundary conditions such that the gauge field of, you've got two gauges, right? So the gauge field of variation 1 is equal to the variation of the other at the boundary. And if you do that, then you don't get G cross G gauge bosons, but G.
I have to look at that. I don't.
In the adjoint.
Yeah, I remember you worked on this problem before.
It's a curious thing that there's like a choice. Normally if you just got Chern-Simons on its own, then it just goes to what you're saying. So you've got two Chern-Simons theories, you could say, so you get that, and that's true. But you've got the possibility, because of the structure of ABGM, to cancel the anomaly across each other.
Okay, we will look at that. Yeah, but anyway, this is just a motivation. It turns out, in my construction of the tensor symmetry, I will have to introduce this gauge boson, but I will not introduce both of them. I will have to introduce one of them, right? I will explain the reason why later. So there's also another paper which is very interesting about M5-brane from the point of view of defining a fundamental definition of M5-brane. So this 5D YAML will be like the BFSS quantum mechanics for the M theory in 11 dimensions. So this is how I think about this this equality here. Okay, so come back to Paris laws. So this is just a standard description of a abelian free-form field string. So H is dB, and these M capital indices are 6-dimensional indices, and then you can have you define Hodge-dual, and the self-duality equation is just that. standard. In the Paris-Ross formulation, there are two special features. The first special feature is that you single out x5 direction. So you use manifest 6-dimensional Lorentz invariance from the start. You only have 5-dimensional Lorentz invariance manifest. And then all the coordinate will be decomposed into the 5-dimensional coordinate mu, and then the 6-dimensional coordinate m, so x mu and x phi. So the theory is written in terms of x mu and x phi. Right? You will not see xm anymore. And then these are just a convention for the metric and then for the epsilon. The second feature about the Paris-Ross theory is that you don't use the whole BMN to represent the tensor gauge field. You only choose a part of it. You represent the tensor gauge field using B mu nu. B mu 5 never appear. And so this, in a way, is like a gauge fixed version of a full theory, if you like. So, for example, if you take you can think about it like YAMLs. You take a Coulomb gauge or take a axial gauge, whatever gauge, and some of the components are missing, and then you write down that theory. So this is more or less like that idea. You write down the theory in that gauge fixed frame. Then this is the action they proposed. H tilde is defined by this. So the tortuosity here, basically, this is like mu nu 5. So this fineness object is due to h mu nu 5, but the 5 is always there, so we just call it h tilde mu nu. If you look at the equation motion of this theory, then you get a second order equation. You get from a second order action, you get a second order equation of motion. That's standard. So this equation will tell you this quantity here, is closed. So that will be equal to this locally for arbitrary alpha. Now it turns out the theory actually has a symmetry of the same form. So it's very easy to see. If you change B by this transformation, H will be invariant because H is just dB. So this will be invariant. So you get something here. So you get H tilde d5 d mu alpha nu, right? And then you can do integration by part and move this mu here. And then this is Bianchi. This is because this is epsilon mu nu lambda alpha beta d mu d lambda b alpha beta, right? So this is Bianchi. So this is 0. So the action has this symmetry. So with the symmetry of the same form, that means if you have arbitrary pieces here, you can always choose a gauge of B, so that this piece can be cancelled by choosing your gauge, by choosing the phi. Basically, d5 of phi is equal to alpha. Yeah. Then you get a first order equation. So this is the self-duality equation in the theory. So this is how, in this theory, you can achieve a self-dual equation of motion. Well, the action you start with is not Lorentz invariant. You only have a 5-dimensional Lorentz symmetry. So it's a question whether the theory actually, or dynamics of the theory actually is 6-dimensional Lorentz invariant. So Lorentz symmetry here, I'm just following their notation. So a standard Lorentz transformation will consist of two parts. It consists of this orbital part, which is basically I'm taking an active point of view. So instead of saying the coordinate are changed, you say I move the field. So these are like the contribution when you do a Taylor expansion in the argument of the field. So you get this. Lambda here is a parameter which is lambda mu with one indices. So it's a transformation which denotes the rotation between the fifth direction and the rest of the space-time coordinate, right? So this is the orbital part, so-called, and then you have the spin part, which just say, well, this will be the common thing you see for transformation, right? So they propose a modified Lorentz transformation of this form here. So this modified Lorentz transformation basically is like taking this part, acting on B. Right? So this second piece is this piece here. And this first piece, you have d5b, but then you use the equation of motion and get this. So on shell, this transformation they propose is equal to the standard Lorentz transformation, the orbital part of the standard Lorentz transformation. And then you don't see any of this spin part. So this is just the transformation you write down, and this explains the connection with a standard transformation, but it's not the standard one, so that's why it's called the modified transformation. If you plug that transformation into the action, then you just do it, and then you will see that the action is invariant. Or there will be a lot of surface term, but then you drop all the surface term by saying all the surface term which involve derivative of B are equal to 0. So then you get the invariance of the action. On shell, I explained already, on shell, the transformation they propose is just the standard Lorentz transformation, the orbital part of the standard Lorentz transformation. If you now do the commutator of two of these transformations, so that means you rotate 5 to mu, or mu to 5, and then 5 to nu, so you should get a 5D transformation within the 5-dimensional part. So in fact, you get that. You get a 5D, standard 5D Lorentz transformation, and then, which is written here just for your reference, and then you get terms which vanishes on shell, and then some term which can be interpreted as gauge symmetry. So this term here is of this form, which for a particular choice of the gauge parameter. So this is very much like what you need to do in supersymmetry, and also in supergravity. You often close your gauge symmetry on shell and plus some other gauge symmetry. So although we are only doing a non-supersymmetric field theory here, but this feature appear in the PS theory. As I said, the modified Lorentz symmetry is very standard for when you want to write down action with self-field dynamics. There are a couple of features about the modified Lorentz symmetry. So to get the invariance of the action, you have to drop a surface term. So this is actually assumed in the theory. This condition, this boundary condition here is assumed not just for the checking the Lorentz symmetry, establishing the Lorentz symmetry of the theory, but also to establish the gauge symmetry. The fact that you have the gauge symmetry in the theory, you also need that because as you can see here in the proof I have given here, you have to do integration by part, and so for those terms you have to drop. You have to assume the field strength as it actually go to 0, which translates to the derivative of B also go to 0. Okay, the modified Lorentz transformation I wrote down consists of a H and then a term which you have a derivative on B, right? This one here. So you can combine. You have this transformation which leaves the theory invariant, but this transformation also leaves the theory invariant. So you can combine these two transformations for a particular choice of phi, not this one, but something else, so that you can rewrite the whole transformation, the resulting transformation, as a expression involving H only, which turns out to be useful. Well, this is very small technical point, but this form also leaves the action invariant, and this is equivalent to the previous form up to a gauge symmetry. Right? So this you can also use this as a modified Lorentz transformation. Okay, this is possible to support a 6-dimensional Lorentz symmetry without. You may think it's crazy. How can we support 6-dimensional Lorentz symmetry without the field actually present there, right? Without this component, because when you transform, as you see in the beginning, the standard Lorentz transformation will necessarily mix this guy into the transformation. But in the modified Lorentz transformation rule here, you simply don't have this contribution. And the reason why that is possible is because of the existence of the symmetry I explained. in the presence of this symmetry in the theory. Okay. Now, are there any questions? Yeah.
One question regarding
Yeah.
the previous delta B mu nu.
Yeah.
So there's a term proportional to x5, right? There's a term proportional to x5 in delta B mu nu.
There's no 5 here, yeah.
The second term, there's a term proportional to x5.
Yeah, x5, yeah.
So doesn't that break translational invariance in that direction? The theory has translational invariance.
No, it doesn't.
I mean, this is not.
Well, I mean, this is just standard Lorentz transformation. I mean, standard Lorentz transformation. You also
breaks
have.
translational invariance along the x5 direction, right?
I mean, this is like you do Lorentz. I mean, you do rotation. If you do rotation and translation, of course, they don't commute.
But
If you rotate, that's rotate with respect to the center, and then when you shift the center, then it's different. So there's a non-trivial algebra there, but there's no breaking of anything in the field.
But shouldn't everything be translational invariant?
Sorry?
It's just a choice. It's an artifact of choosing 5, right? But this is not invariant under shift of x5, right?
Yeah, this transformation is not invariant. As I said, just the rotation and the translation, they don't commute, as usual.
That's true, but
Yeah. So this is standard. This x5 appear also in the standard Lorentz transformation. Also, you can say appear in the standard rotation. Also, so there's really nothing.
why do they write in standard?
Huh?
In a Lorentz invariant theory, you never get. I mean,
This is a standard Lorentz transformation. This is standard Lorentz transformation. It's there. I mean, there's nothing special about this.
so that comes from x mu del 5 minus x5 del mu. That's part of a Lorentz covariant structure in 6 dimensions.
Yes.
But this one did not have an analogous 6-dimensional part. I mean, this is the term x mu del 5 minus x5 del mu, right?
Yes.
This term. So that's part of some.
But your question is just whether this commute.
So this is Lorentz covariant from the 6-dimensional point of view.
Yeah.
That one is not Lorentz covariant from the 6th.
Well, that one is. If you ask that question, that one is equivalent to this after the equation of motion term. That one is on shell. So if you look at the symmetry, you always look at the symmetry on shell. So when you look at the equation of motion, then there's also no.
I mean, this is only the potential, right? So then you've got to take the exterior derivative of the field strengths, and then it all works out fine.
But it's something that, but for the potential, shouldn't transformations be gauging? I mean, for very even in field, even in say photon.
It's a very simple thing. If
You've got to impose a self-duality thing.
no, I think that's not. It's simpler than that. Yeah. You can check it. What I want to say is, what I meant to say is, you worry about whether the symmetry,
I'm just worrying about at the end.
whether the equation of motion or that.
A 6-dimensional Lorentz symmetry.
Yeah, whether the equation of motion, for example, there are two ways you can, two things you can check. So first you can check whether the equation of motion are translation invariant, right? Well, obviously it is.
That is manifest from the action.
Yeah, from manifest. Action or equation of motion is manifest. And then you can check whether the action or the equation of motion are Lorentz invariant. That's also manifest. And then you can ask whether the commutator form a group, right? So the answer here, I think I understand your what you want to ask. The answer here is that this is a modified Lorentz transformation. So we have additional symmetry here, which is a gauge symmetry. So in fact, they don't close in the standard sense, but they close up to this gauge symmetry. So the Lorentz group, now you cannot talk about the Lorentz, with this modified Lorentz transformation, you always have this additional gauge symmetry in the background. So they close up to this gauge symmetry.
Could I
Yeah.
if you were to do this with PST,
Yeah,
so this is like gauge fixed PST.
yeah,
And if you were to do the sort of thing you say,
yeah,
then you could sort of undo it with a PST gauge transformation.
yeah, I think so. Okay, yeah, the X5 really have no importance. Here, yeah. Is it okay?
The thing is, it's fine, but it's not manifest, which is your problem.
Yeah, probably it is.
Which is, with all these Lorentz symmetries and everything,
Yeah.
it's not a manifest symmetry in the action, so all your intuitions have disappeared with it. You have to actually calculate equations of motion or whatever it is, and then check. Right. Or at the quantum level, it's even worse. There's a potential anomaly. And you have to check that these things go away.
Yeah.
Even Lorentz symmetry is not
That's
met.
true.
Even Lorentz symmetry is not manifest, right?
Yes.
The 6-dimensional, there are 5-dimensional part that's manifest. The Lorentz symmetry I'm talking about here is the one which makes the fifth and the rest. That part is not manifest here. That part is there by you doing this modified Lorentz transformation, but then it doesn't look like a Lorentz transformation at all, as you can see here, because standard one you have a d5 b, but then you have h2 here, right? But if you go to the commutator, then in fact you get the 5-dimensional Lorentz transformation plus all this stuff. So in a sense, it's a standard Lorentz transformation. Yeah. So the idea, after doing this exercise, the idea is to give up manifest Lorentz symmetry, and also to represent the tensor gauge symmetry using a set of 5x5. Yeah, using a set of 5x5 b mu nu, and then introduce a set of gauge field for the gauge group. So in the G cos G, I would introduce two sets of gauge field because there's G cos G there. But in the construction which I'm doing here, I will only introduce one. I think eventually maybe one still have to use this G cos G and introduce two. The construction there with G cos G is Lorentz manifest Lorentz invariant, the whole construction of the symmetry. But here since we give up 6-dimensional Lorentz symmetry, so there's no reason why we have to introduce two. I mean, so in the construction I will only introduce one. But I think it also suggests in the PSD-like construction probably we have to do something like that. But that's something I haven't looked at. Now the action is a very simple generalization of the PS form action. So the field strength is just you just take the covariant derivative, where the A is the gauge field I introduced. So at the moment, it seems we have too many degrees of freedom. But at the end, I mean, I will actually the theory will actually turn this A into auxiliary field. So A is not an independent propagating degree of freedom. It will depend on the rest of the field of B and H, etc. So the degree of freedom will be okay. So in this formulation, so far, I have no B mu 5 and no A5, right? And the A mu, I will take it to be living in 5 dimensions. So this is a weird thing, but later it will see it come from the constraint of the theory. The action is obviously gauge invariant under Yamu's gauge symmetry. So ordinary this means the covariant derivative, and then the B transform into adjoint, and then the field strength will transform into adjoint. And then you also have a tensor gauge symmetry. So this gauge symmetry is B transform like a shift, but the shift is constrained, which is D sigma equal to 0. So in the abelian case, this is just saying sigma is closed, and then locally sigma is exact. So you reproduce the previous gauge transformation for the abelian case. The non-abelian, so I think you can write down something like, if you want, I mean, we can maybe write here. We can write something like this, and then say alpha F, right? So, and say this is the symmetry for B, but these two are really equivalent because I don't really have a solution of alpha without using the constraint. So in any case, I have to write a constraint. So I can either write like in terms of a sigma, or I can write in terms of a one form alpha, but alpha is constraint, and these are equivalent. So let me just write it in this form. And then the action will be looked at by assuming the covariant derivative vanishing at infinity, right? To establish this symmetry, you have to do this. Now then, the tensor gauge symmetry is abelian by looking at this, or you can look at this form here. And Nevertheless, the system will turn out to be fully interacting. Okay, that's not the whole story. That's just one action suggesting from a PS action. So as I said, we have a mu in the game, and we don't want to have extra degree of freedom from supersymmetry. So we need to impose a constraint. So the constraint is suggested by this consideration. So h goes to 0 at infinity. That means at the infinity, h, which is dB, right? So if I identify f with the boundary value of b, then f will satisfy the Bianchi automatically as a result of this. So it turns out I would impose this constraint instead of just saying f is the boundary value. So I would impose f as an integral. This is for the reason that when I do reduction later to 5 dimension, I want to get the Young views. So this is important to have this integral constraint. So I will impose this integral constraint by introducing auxiliary field again in 5 dimension like this. So f and E are both 5-dimensional field, and h integrated is supposed to be equal to f. Now the action this action has a Young symmetry and the tensor gauge symmetry, and also invariant under a shift of E when if the parameter satisfies this condition. The first condition is needed because when I do a shift here, okay, the first condition is to get rid of this term because of then you can use the Bianchi. The second condition is to get rid of this term. Yeah. So now I look at the equation of motion. If I integrate out E, then I get this constraint which say f is auxiliary. So I don't have any additional degree of freedom now in A. And equation of motion of B give me this equation. So you have the additional contribution from the action of E. So you have this additional term here. Now normally, I mean the PS, this is the main difference with the PS case. In the PS case, you don't have this term here. Now, but this term actually is we drop out. I mean we can see it here, because if you integrate this equation on x5, then you get three contribution. The first contribution here, when you integrate with x5, then you get f again, and then because of Bianchi, that term will drop out. The second term here, you get integrate with, so you can exchange the derivative of 5 and d rho. So then you use that to construct the field strength. So the second term, right, this is like h, and then we integrate over x5. So that will give you h at infinity, basically, and that's 0. So that's also taken care of. So the only thing you have is this last term here. But then since E is a 5-dimensional field, so what you have will be just dx5 right, and you say the whole thing is equal to 0, but this is independent of x5. The only way it can work is that this is identically equal to 0. Otherwise, it will get infinity. So this term also drop out. So you get to this. So this now you can run the same argument as in the Paris-Walsh. So this has a solution. General solution will be like this with a phi satisfying this. And again, then you can because of the symmetry in the theory, B has a shift symmetry, which is precisely with a parameter which satisfies the same condition. So by choosing that parameter, which means it's gauge fixed, do a gauge fixing, then you can get rid of this phi term, and then you arrive at a first order self-duality equation of motion in the theory. So we still have equation of motion of A. So that will give equation of motion for E, right? So that will give you tell you what E is. But actually, the we don't really need to know what E is because if you look at the equation of motion, basically we have this equation of motion, which say F is function of B, and then we have this equation of motion, right? So these two equations of motion never talk to E. So it's enough for you to look at these two equations of motion and then solve for the dynamics of B. And then after that, then you can substitute into the last equation and then solve for E. Right? But then E doesn't talk to B and A at all. So it's not important to have this equation. Now come to the counting of the degree of freedom. So we have apparently we have E, which is too many, right? We have B and A and E in the theory. A is function of H, F is function of H tilde from the integral constraints. So we still have E. So let's go back to the abelian theory and just remind ourselves how the counting is done, right? It's a simple exercise, but it's quite instructive. So in the PS theory, the abelian theory, so this D should be the usual D. I mean, there's no covariant D here. You have the equation of motion, and then using the gauge symmetry, we said that we can gauge it, and so that that becomes this, a first order equation of motion. After you have done the gauge fixing, you are left with an X5 independent residual symmetry, because the way you come from this second order equation to the first order equation is, as I explained there, you have to so this equation, say this is equal to d lambda phi sigma. And then the symmetry of, so you can get rid of this term if you choose alpha sigma b5 equal to this. Right? This is a gauge fixing condition for the parameter. So after you fix the gauge, you arrive at the first order equation, but then that also means the alpha, the fifth dependence of the fifth direction is already fixed. So you are only left with a X5 independent gauge transformation. So you have an X5 residual independent residual gauge symmetry in the theory. And that is precisely what you need also, because first of all, you can check that this quantity here is X5 independent on shell. It's very easy to see, because it's simple to do. That's why I choose to do it on the blackboard. Right. On shell, you can use the equation of motion. That means this is H mu nu, right? And then this is Bianchi. So we know this is equal to 0. So this quantity is X5 independent, but then precisely we have a residual gauge symmetry which is X5 independent. So we can use that gauge symmetry, which is a parameter with it's a one-form parameter. So this is a one-form condition here also. So we can precisely use that gauge symmetry to make this equal to 0. And after that, that means you have a condition. You have 5 equations here, but in fact there's only 4 independent conditions here, because this equation basically tells you in the momentum space you have a p, and this vector here, if you expand in terms of in terms of basis of vectors, then you have 5 components, but one of the components is in the direction of your momentum p, and that component is not constrained by this condition, because obviously if you differentiate again, then you get nothing there, right? So in fact there's only 4 conditions here. So from 10 components of B, you have only 6 independent components, and then the self-duality equation half it, so we get 3. Is it okay? Now I choose to do this because I don't see this kind of thing in the literature, but I think it's quite simple to see it explicitly. So that's why. Yeah.
Before you do that, can you go back? There's just before that slide, there was a thing about one more back.
Yeah.
I think
This one.
There was a statement somewhere which I'm trying to absorb about gauge. Actually, it's the slide before that. Sorry.
Okay.
Yeah.
Yeah.
So
About
F mu nu is identified with the boundary value of B mu nu.
Yeah.
You say at the top.
Yeah, that's a suggestion, but actually I'm not doing that.
But you're not doing that.
No, I'm not doing that. Yeah.
Okay.
Yeah. So I mean that would be what you get from here. But I'm doing this because what I want is actually on shell this will give the same thing. On shell I can substitute this by D5 or B.
I'm not sure it is the same. But if you're not doing that, maybe.
No, I'm not doing that. No.
Okay.
Yeah. On shell, of course, on shell it's not the same, precisely the same because I'm looking at this constraint not in the action, in the context of
I
action.
mean, I was just thinking of large gauge transformations. Can be physical, and then it would be.
Okay.
But no, if you're not doing that, then.
No. No, that was just a motivation. Maybe I shouldn't even put it there. It doesn't motivate. Good enough. Okay. Now, how do I count for the non-abelian case? So, I would do the counting just like you do in field theory, Yang-Mills or any interaction field theory. So you count it by taking the higher order terms as interaction, and then look at the quadratic level, and count the degree of freedom at the quadratic level. So at the quadratic level, the action consists of two parts. The non-abelian Paris-Source action, which just reduced to many copies of the Paris-Source action. Precisely how many copies depending on the dimension of the group, right? And also we have the action for which implement the constraint. So for the Paris-Source part, we know the counting is just 3 for each copy, so we get 3 dimension G for the B mu nu. Now for the E, we don't expect any degree of freedom in E because it was just a auxiliary field. You integrate it out and then to get the constraint. So, but we can also see it directly here because the linearized equation of motion for E. So we have two equations for E. One is the equation of motion. This one here. So at the linearized level, this is just the ordinary derivative of E equal to 0. And then this one here, again, at the linearized level, all these terms drop out, and then you just get dE equal to 0. But this, we also remember E has a gauge shift symmetry with the parameter which satisfies exactly this condition, right, at the linearized level. So we can use that symmetry to remove E directly. So that means at the linearized level, that when you look at the degree of freedom, there's really nothing left apart from the degree of freedom in B. So we get this degree of freedom, and which is what you want from 2,0 supersymmetry. So here I haven't restricted the group to be anything because at the moment I haven't. This is just a theory in 6 dimensions, and I have not made any claim that this has anything to do with M5-branes. The connection with M5-brane will come later. When I look at the dimensional reduction, if I can get something close to D4-brane, that will suggest or make some evidence, give some evidence that this has something to do with M5-brane. But that will be the next part. But before that, I want to establish the Lorentz symmetry. The Lorentz symmetry is a more complicated story here. So I don't know how much I want to give you the details, but it's in short term, it's just complicated. Yeah. So if I look at the general variation of the Paris-Source action, then it turns out we take a very simple structure. So there's a H tilde times this delta. Delta is like you take the B as it's like computing the anti-self-dual component of the field strength, where delta B will be the field strength, something like that, right? So in any case, this is a general statement, right? So now I take the 5D Lorentz transformation. This is the original Paris-Source or the modified Paris-Source transformation, where everything written in terms of H. And I put an additional parameter lambda here, just in case I need it, right? It turns out I need it, actually need it. And then so in the very start, you can just try to put the Paris-Source transformation with lambda equal to 1 and try to see whether this action at least is invariant or not. Then you discover it's not. And if I put a parameter lambda here, just in general, just to see how it depends on the different coefficient, and then you see that this part of the transformation will give you a pieces like that, right? Which is not invariant. So in the case of in the abelian case, this will be invariant. If you choose lambda equal to 1, that term will drop out, and then for lambda equal to 1, and this you can use the Bianchi identity and then do a little bit of thinking, and then you can get equal to 0. This is what Paris-Schwarz did actually. So for here, then it's not 0 because the Bianchi identity for H actually is non-trivial. So to make S 0 invariant, so let me put a additional transformation there, right? And then see what happens. So if I put additional transformation, then the action will be invariant if this delta B, which you produce from this one, cancel what you have here. But this part is what you get from the first piece of transformation. After a lot of cancellation, then you get to that. Right? So you get an equation which implicitly, I mean this is like a differential equation which implicitly determine phi in terms of H. Right? So it's now first of all, you know this is just a first order differential equation. So if you think of phi as a time, then you can always solve it. Right? So there's always a solution. So you can at least then claim there's an existence of a modified Lorentz symmetry for the S0. I mean, of course, we still have to look at the other action S of E, but at least for this part, then at least you can say there's an existence of the symmetry. But actually, we can do better. Yeah.
So exists even for a single M5 brane. This is a new symmetry for a single M5 brane.
No, for single M5, no, it's not a symmetry. I mean, it's not a new symmetry. I'm just trying to compensate the transformation to see what kind of compensating transformation I need in the non-abelian case to have a symmetry. Yeah. No. Yeah. So in the single M5 brane case, you don't need this.
But is it still there or not?
Which?
I mean, this symmetry transformation, this delta B mu. I mean,
this one?
The next one, yeah, this new modified.
Yeah, in the abelian case, you can solve the whole thing, but then you don't need this because this is already equal to 0. So you don't need the phi.
But if I have it, I mean, suppose I keep it. I mean, it's still a symmetry, right?
Suppose what?
Suppose I keep the last term, this lambda k phi mu.
Yeah.
But
you'll find the phi equal to 0.
But that's the only solution for it.
No, I mean okay, I see what you mean. You mean this equal to 0, and then try to solve that equation with this j here equal to 0, and then yeah, I mean you can do that, and then I think you will find that phi will be given by gauge transformation, so there will be gauge symmetry. That means you can always modify the Paris-Schwarz transformation with additional gauge symmetry, but that's not.
In other words, for the single M5 brane, this is not giving anything new. I mean, this is
no, it's not anything new. No, not anything new. No. Yeah, I mean this is for the non-abelian case you need this, but it's not a new gauge symmetry. It's just another way to write the Lorentz symmetry, but I have to write in the non-local form. But we just have one single Lorentz symmetry here.
I was just going to interrupt you. Put this extra term would have been lambda minus 1 factor. So when we take lambda equal to 1, this.
I mean, why do I take lambda equal to minus 1?
Lambda minus 1.
Yeah, I need to make lambda equal to minus 1, in fact.
Yeah, no, in the gauge transformation that.
Yeah.
Lambda k phi mu k.
Yeah.
Would you have an extra lambda minus 1 factor? So when you take lambda equal to 1, that's trivial.
Yeah. So okay, I see what you mean. Yeah. Yes. If I take this lambda here equal to minus 1, right? For lambda equal to 1, this is the standard Paris-Schwarz, and I don't need any of this. I can also choose to write lambda equal to minus 1, so this is not the standard Paris-Schwarz, and then I have to compensate it with additional term here, and then you can solve this equation, and then after you solve it, then you will find that in fact you will find a solution which with twice of this time, so you turn it back to the minus 1 again, plus the gauge transformation. I mean, I don't know if I want to enter into these very details. This problem exists only if you have read the paper already, I think. I try to avoid by not mentioning it. Alright, you can solve, this is only in the second version of the paper. In the first version, we were happy that the symmetry exists, but actually you can do better. So you can use the green function method. So it's just solve the same equation with the delta source. So there's a green function there. And then you can decompose the solution as a green function, which is for a standard problem. Integrate over the term which you need to cancel. So we have an explicit and integrated form of the Lorentz symmetry. Now, we also have to take care of the SE. So for that, that's the reason why we have to introduce the lambda there. So for technical reason, again, you have to choose a lambda equal -1. In that case, then if you also take the E to transform under this, then everything will work out. The total action will be invariant. So there are two quite important comments. First of all, the Lorentz invariance of the action immediately implies the equation of motion are invariant. Right? That's standard. But here we are actually talking about two kinds of equation of motion. One is the original one, like this one with a coherent derivative, which is second order. And also we have talked about the first order self-duality equation of motion, which is obtained by gauge fixing. So there's no reason that the self-duality equation of motion, which we obtain by gauge fixing, is still Lorentz invariant. It was the case in the Paris-Ross case, in the Nonabelian case, but in general, there's no reason for that to be Lorentz invariant. In fact, you can check it and then it's not. So this is actually not surprising. It's not just like you take Yamil's equation, you take a Coulomb gauge or whatever gauge, and then it's not gauge invariant. It's not Lorentz invariant, the equation of motion. But I want to emphasize that this remark could be important because I think so far people have been trying to supersymmetrize things and by looking at the equation of motion, which is a self-duality equation of motion, and trying to supersymmetrize that. But I think that has a danger because from this here we see that the equation of motion for self-duality equation of motion actually is not Lorentz invariant, and so it's not directly compatible with the supersymmetry. So it may be, I mean, the self-duality equation of motion certainly is important for doing counting of degree of freedom, but for supersymmetry maybe we have to look at the original equation and gauge fix the equation of motion and supersymmetrize that one instead. The Lorentz transformation and the action we propose are non-local. It may sound strange, but I want to just give a couple of remarks to ease your feeling. It's not so strange because, for example, just like QED in Coulomb gauge, it's non-local already. I mean, you have a non-local interaction between charges. So here we are working in a formulation without B mu 5. So it's very likely, I think, that all this non-locality is artifact because of we are working in a formulation like a gauge fixed combination without B mu 5. Also, like the Lorentz transformation again is non-local, and it's like in string theory. I mean, you go to Lycombe gauge, and certainly Lycombe gauge is not Lorentz invariant, but then you can keep the Lycombe gauge if you do a compensating diffeomorphic transformation, and that's non-local, right? To restore the gauge. So it would be interesting to see if this is really the case by doing the PST construction, and maybe that will, with the additional auxiliary field in the theory, in the PST construction, then it will allow for a local representation of the Lorentz symmetry. I don't think you can avoid the non-locality in the action because of the local theorem in the literature. But at least for the Lorentz transformation, there's a chance in the PST construction it may be local. Finally, about the reduction. So the reduction is actually quite simple. If you competitive on X5, you integrate over a circle, then you reduce to a 5-dimensional integration. Then you get R in front from the measure, and then everything doesn't depend on X5. So the piece of action which depend on X5 dropout, you only have this from the Paris-Ross action, and this is what you get from the constraint action which implement the constraint. So if you integrate out E directly, so this is the place why I want this integral constraint instead of saying F equal to boundary value of B, because that would not work for this reduction. But if I have the integral constraint, then I just get a factor of R in front of h tilde, and so that would mean if I substitute h, you might, after I integrate out E, right, then this is precisely f squared. So that's Yang-Mills. And then if I want this to correspond to D4 brane, that means my gauge group has to be UN. So that means the M5 brane, for n M5 brane, the action I obtain should be based on a group UN. Now, but that's a small puzzle. I mean, if you look at it more carefully, so because the equation of motion of the Yang-Mill will tell you this, just the equation of motion for the Yang-Mill. On the other hand, because of the constraint F is equal to h tilde, and then because of the longitudinal Bianchi identity for h, then you get a longitudinal contribution. So this is not compatible certainly. So something is wrong. It took me some time. Took us some time to think about what is wrong. It's quite simple. If you do a careful path integral analysis, then basically you integrate E first, then you get delta function, right? Then you integrate B to implement the delta function. But the fact is that this delta function is not delta function low is not a constraint on B directly. It's a constraint on the derivative of B, and so you have to solve this. And then there's some longitudinal measure factor, which one can do, but I don't know how to do it yet. But eventually, you will get additional contribution, just because the integration of this thing here is non-trivial. And by consistency, but one thing we know is that by consistency, this contribution must reproduce what you have in the constraint already. Right. So this is like a consistency condition, which I don't know, maybe it's strong enough, allow you to solve S time directly. So we are looking at that. So the 5-dimensional theory at the end is given by Yang-Mills plus this correction. And this correction here actually looks like a higher order derivative correction because F is like 2 derivative already, and B, because of the constraint, and is of the order of F already. So this looks like a high derivative correction. It will be remarkable. I mean, it will be very nice if this actually has something to do with the DPI action, because nobody tells you have to get exactly just Yang-Mill in the lowest energy from the reduction. Just like M2-branes, I mean APJM or BLG, you don't really get the Yang-Mill. I mean, you can get Yang-Mills plus corrections. So okay, finally, so I've constructed an action. We have constructed an action with this property. So the proposal is that this actually describes M5 brane in flat space. I have not included supersymmetry. Interesting question is what is the scalar potential? I mean, we have supersymmetry, then you can include you have the scalar field in the theory, and then you have the scalar potential, and you can ask what is the BPS equation. When you have a BPS equation, then you can basically do a lot of things. I mean, compare with supergravity, like the Parshall-Harvey equation type of analysis. It will also be interesting to think about what's the connection with the other proposal. I call it 5D Yang-Mill proposal of Douglas and Lambert, Douglas and Summerfield. Yeah. As I said, I like to think about this proposal like the BFSS matrix model proposal for M theory. So in that proposal, one of the major issues is Lorentz invariance. So here we have the issue about how do you recover 6-dimensional Lorentz invariance from a 5-dimensional Yang-Mill, right? But it's not an attack, but I think these are important issues to think about. Another issue is how do you recover the B-mu-nu from the 5D Yang-Mill, just like how do you recover gravity field dynamics from the BFSS matrix model, right? All these are interesting. So one thing this work I described today provide like the gravity description of this story. So in principle, one can then compute the amplitude or scattering or whatever process involving the B field, and then compare with the S. I mean, if one is able to identify, get the dictionary of B field in the super Yang-Mill description, then one can start comparing, and then maybe get some interesting story. So I think finished. Yeah. Thank you.
Quick questions.
Yeah, a couple of questions.
So one is basically your small a in the trace.
that basically
Small a in the tray.
in the tracer you had this small a, right? B mu the subscript superscript small a, which was
Yeah.
so that goes from that basically goes from 1 to in other words that basically counts the number of M5-branes, right?
No. That's a.
Because that gives you the gauge index in 5 dimensions.
Which index is
So
it?
in other words, this small a went from 1 to dimension of g, right?
You mean this is?
Yeah.
Yeah, this is 1 to n squared.
1 to n square.
Yeah. I mean, just like Yang mu, I mean, you have n
Yeah. So
squared.
then basically, from this theory, how can you ever get more than n squared degrees of freedom?
I get n squared, yeah.
But you'll never get n cubed.
I want n cube, yeah. I don't know.
But how will say it doesn't seem to me that this can ever give you
Well,
more than
you don't know.
You don't know.
Because it's interacting. You
Yeah,
can't just
counting number
count.
of fields is not the same.
You can't count the fields because it's an interacting theory.
Yeah.
So it's one couple.
but interacting it's
So I don't know. I mean,
adjoint. So how can you get more than n squared?
yeah. Just recently, there's a computation of index of the 5D Yang mu. They also get n cube.
Yeah.
So I don't know the details of that computation, but there's an interpretation. I mean, there's a picture which count how many times strain causes a brane, and that could give additional factor of n in that story. But
It's misleading just to count the fields.
It's
and
misleading
I mean,
to
it's
count,
just lucky in n equals 4 Yang mils and it's 3/4. I mean,
yeah, but I think it's certainly right. It's more longitudinal. How do you get more out of n squared? But
Another thing which I wanted to ask you, for example, if you took it on an S1, you could have taken it on 2 S1s, right?
yeah, you can compare the 5 in 4
4
dimensions.
angles, and
Yeah,
I think the argument is that for one the
you get some S duality.
R,
Yeah.
the other should be proportional to 1 by R, so that you get S duality of n equals 4 angles.
That would be interesting.
But
also.
here will you? But you get. But here, how would you get that?
Well, first this formulation has a very specific choice of direction, which pick up x5 already. So already, if you take if you compare x5 and then compare by another x mu, x4, let's say, you cannot see this. I don't think you can see this because the two directions are treated very differently. I mean, even here, if you compare by over x4, just on one circle, it's already not clear how you get to Yang mu. But you may go to a covariantized PST formulation, and then it will give you a more covariant way to do the compactification, and that's work.
if you go to PST, you've got this auxiliary field,
Yeah.
and basically, depending on which cycle on the torus you pick the auxiliary field to point, that gives you the S-duality transformation.
But here's not obvious.
So here is picked 5, and
Yeah.
that's like picking the PST direction to be 5, and that picks you an S-duality frame if you go on the torus. So you've got to reintroduce PST, so that if you covariantize, as he says,
Yeah.
the projection, and then depending on which cycle you go on the torus with your auxiliary PST field, you'll generate the S-duality transformation. That was my PhD. I was working it out 15 years ago.
But not for the Nonabelian.
Not for the Nonabelian.
So that will be your PhD.
Not for the
will do it.
Nonabelian. That was what I did.
You're still
15 years ago.
Yeah.
You were working on this 15 years ago as well, weren't you?
Yeah, similar.
Yeah.
And then one very very nice question.
Yeah.
So basically, suppose you just took say Yang mills,
Yeah.
and you didn't know the Nonabelian part. In other words, you just took the U1 part. Just say minus 1/4 F mu squared in 4 dimensions.
Uh-huh.
That's the U1 part. And suppose you had to do this same kind of analysis.
Uh-huh.
You took it down one less the dimensions and so then basically, I mean, would you have discovered? That would not have given you Yang mills, right?
Which one? You mean this one?
I mean, suppose you did exactly what you did for just U1 gauge theory in say 4 dimensions.
You do it for U1, you will get exactly the PS, and then you will get exactly the U1 in 4 dimensions.
No, but you would not discover Yang mills, right?
Or in 4 dimensions?
Yeah, I'm just saying. I mean,
Okay.
I'm just saying. Is it obvious that this theory?
I think you will, yeah, because you can do it first on x5, and then you can reduce it again.
Just 4-dimensional say U1, just 4-dimensional U1 electrodynamics.
No, I don't know what you want to do. You want to do it from this theory and then reduce to 4 dimension?
No, nothing.
No, forget about this theory.
Nothing about this theory. I'm just
Yeah.
asking. So what you did was you took the abelian version of the theory and basically put in some extra indices and went one direction lower, right? And did something non-covariant there. So my question is, suppose we just did not know about Yang mills, we just knew about U1 gauge theory in 4 dimensions, just electrodynamics.
Yeah, you get that.
I mean, would this kind of a construction give you Yang mills? The answer is probably no.
You're doing U1, so I don't see why you say Yang Mills.
Yeah.
Now, let's suppose you wanted to discover,
You want to discover Yang Mills starting with an abelian theory.
so that's what I'm saying. I mean, is this obvious that this?
This is not what he's doing.
Huh?
He has Nonabelian theory, and then compactify that.
Yeah.
So there's no way you would discover Young Mills. I think.
I know. So that's what I'm saying. I mean, so,
No, but this is
so
not
could
what
there be a
he's doing.
different? But could there be something?
I don't know what you want
Different
to do.
construction to get to. I mean, M5-branes. I mean.
I don't want
Maybe we should discuss later.
Yeah,
I'm going to ask one question.
Yeah.
So you had to integrate over x5,
Yeah.
and you wanted so therefore you wanted a boundary condition on h.
Yeah.
Because now, if I just look at the solutions that I know exist
Yeah.
in the theory, then, for example, the self-dual string doesn't have a boundary condition that it. I mean, I can align the self-dual string along the 5 direction, and then that integral won't vanish. It will give you infinity.
Yeah.
So for the self-dual string itself, it wouldn't be consistent.
Yeah. The self-dual string solution already exists for the Paris-Schwarz action.
Yeah, yeah.
So the question then you have to ask them.
Yeah, so exactly. So I know that solution exists
Yeah.
for the Paris-Schwarz action.
Yeah.
And now if I put your formalism with that solution,
Yeah.
I get singularities everywhere.
So what kind of boundary condition you get for the
Well, no, it's dead simple because the string is aligned. So I align the self string along the 5 direction.
Yeah. No, but we don't have scalar here, so
You don't have a scalar.
no, I don't have scalar. The self-dual string equation. we
Not Paris-Schwarz solution. Paris-Schwarz solution is without scalar. It's a soliton.
have- Okay.
It's a bump finite.
Uh-huh.
And then, so it's a finite bit, which is fine. That was nice. But then you can align it, the string direction along x5.
Uh-huh.
And it gives me infinity when I integrate along
Well,
x5.
I don't know.
Yeah, well, it does.
I've looked at the construction again.
It's a string, so it's got symmetries along
But this is
x5.
the same type of boundary condition. They would have their theory also. I mean,
It won't solve. It, okay, well,
I mean, it will be a question for them. But we have to look at precisely the solution. I suspect the field strength itself or the derivative we are taking probably will still be okay. I don't know.
no, I mean the field strength. I know exactly what it is. I mean because
Is it
it's
zero? It's not going to
it's
zero.
h012 is equal to some function is equal to
Uh-huh.
h345, which is equal to some function, and then this function is like they had to integrate it numerically, but it's like a sesh squared type bump.
Uh-huh.
And then that's it. And then it's a string solution, so there's symmetry along the direction of the string.
Mhm.
So I can pick that to be x5.
Yeah. So that's not going to zero. You say the derivative of that b.
No, definitely not.
Everything.
Definitely not. So, I mean, it could just be that. I mean, it could be, the point is to go down to Yang Mills, you normally put that on a circle and then it'd be finite.
I mean, this question has nothing to do with quantification. It's already
No, exactly. So I'm
Yeah.
saying if you're
I
not.
mean, even in the reduction from the second order equation to first order equation, you need this boundary condition.
I mean, yeah, I'm just saying that if you are compact, it's still fine with Yang Mills.
Yeah.
And indeed, that will reduce just to some, finite mass object.
Okay.
But if you're not compact, then you know you have solutions
Mhm.
that have string solutions, which means there's isometries along the x. I mean, that's almost by definition. You want string solutions,
Yeah.
which means you're not going to integrate to 0.
Yeah. Sounds very strange.
Anyway,
Okay.
go on, one more.
This about supersymmetry. Since you are claiming that in 5 dimensions you are going to get super Youngness,
Uh-huh.
so with self-dual tensor fields in 6 dimensions,
Is what?
with self-dual tensor field
Yeah.
in 6 dimensions you will expect 2, 0 or 1, 0.
Oh, well, of course, I would like to have 2, 0, but I think, learning from the story of M2-branes, it may be too much to ask for 2, 0. So maybe at the end it's 1, 0, and then there's some non-repetitive argument, some mechanism which enhance the symmetry to 2, 0.
The other point of view is there something which is non-trivial, non-particular.
I don't know, yeah, but I think it probably would be too difficult to construct 2, 0 just because of the lesson we learned from M2-branes. But that's not a strong statement. I mean, once you try, in fact, we are trying the 2, 0 at the moment. Yeah.
But in the case of PST, what was the what is that supersymmetrization to 0 or 1?
2 0,
2 0, yeah.
Why we, okay, so you were saying that maybe in your formulation, you may not explicitly say 1 0, 2 0, but
Yeah,
maybe
yeah.
1 0 and then some enhancement.
Yeah.
He needs the scalars to do it all
Yeah, that's
properly,
what-
and then he's not
There's
discussing
a,
it.
there's a complication with the Nonabelian and all this normality. Yeah.
All right, it's getting late. Let's thanks, speaker. Very interesting talk.
Thank you.